So let's think about this subset here of R2, all right? So S is the set of all these vectors, and there's infinitely many of these vectors. So now, coming over here, I mean, let's just get a picture of what's going on. So S is equal to x comma 1/2 x, right? So the second component is half of the first component of each of these vectors. Well, what does that mean? I mean, if you have like 1, 2, 3, 4, 5, 6, 1, 2, 3, -1, 2, 3. We can get a trend here is in -1, -2, -3. And let's draw some pictures. It's always fun, right? So one potential vector, if x was 2, the second component you'd have the vector 2, 1, right? That would be the terminal point to that one. I'll make the illustration larger in a second. And just continuing on with some other possibilities, if x was -2, you'd be at -1, correct? And so this would be another vector. If x was 6, where would we be? Over at 3, right? And so on and so forth. There's infinitely many vectors along this line, right? So, all right. And what would that line be, just for fun? I mean, this line would be 0, 0 is the intercept, right? So y is equal to, so for every 1 we go up, we go right 2. So our slope would be 1/2 x. Looking at it as a line, all right? We're dealing with vectors, but just to give you a feel for it. Let's check this out, all right? We want to see, is S a vector space? Well, at this point in time, with what we know, this is the long way of showing something as a vector space. So get ready, because this will seem a little intimidating, but it's really just doing proofs like we had done before. So we need to pick vectors from the space, right? So we'll let U equal to U, comma, beautiful, 1/2 U. We don't need to use numeric subscript, right? Because if we name them different letters, right? Because the second component is in terms of the first. So, all right, we can let V equal to V, comma, 1/2 V. W equal to W, 1/2 W. And notice the difference here, okay? I don't have arrows over the components, right? I only have arrows over the vectors. Such that U, V, and W, these components, belong to the real numbers, and let C and D also belong to the set of real numbers. So now we're all ready to go. If you don't feel confident enough to outline that right away, it's okay. All you have to do is you just need to go ahead and leave some space up top, and if you find out you need another vector, just add it in, all right? So closure under addition. would you agree that our vectors u and v belong to the set S? We have them in that format, correct? So now we need to see that what u plus v is. So u plus v is equal to, in component form, u comma 1/2 u plus v comma 1/2 v, which is u plus v, again these are just real numbers, comma 1/2 u plus 1/2 v. Now we haven't quite done it yet because we want to have the 1/2 factored out to show this. We need it to be exactly in the same format. So this is equal to what? Beautiful. U plus v, comma, 1/2 times the quantity u plus v, because the real numbers are distributive under multiplication, right? So this one was by definition of vector addition. This is because the set of real numbers is distributive under multiplication. And then continuing, what would we say? Which is an element, I'll put a comma here, which is an element of S. And so we're done. We've shown that when we add any two vectors that are from that set, okay, we get a vector that's part of the set. All right, so next we have commutativity under addition. So commutativity under addition, what do we have to show? Good, we want to show that u plus v is equal to v plus u, right? So start out with u plus v. Well, in component form, that's u comma 1/2 u plus v comma 1/2 v. Now by definition of vector addition, we have u plus v comma 1/2 u plus 1/2 v. Now this time we don't need to use the distributive property on the 1/2 because that's not where we're going. We're going to split these vectors again. The reason we can do that one is because of definition of vector addition. All right, so next up, this is equivalent to v plus u. Remember, we're in the real numbers now, so we can use the commutative property to commute these terms in the sums. And we can do that because the set of real numbers is commutative under addition. Now, this one will be equal to, if I split them apart again, right, I'll have v comma 1/2 v, so I'm using the definition of vector addition backwards, if you will, plus u comma 1/2 u. And then bringing it home, what does that equal to? That will equal to v plus u, which is what we were trying to show. Groovy? All right. for associativity under addition, we are going to need how many vectors? Awesome, 3 vectors. So again, we've already set everything up. So if we have U plus quantity V plus W, all vectors, I want to end up with the parentheses around U plus V at the end, and then I'll be done. So let's do it. Let's start out by putting everything into component form. So we will have U, comma, 1/2 U. Note that this is now just U, the real number, not U, the vector, plus the quantity V, 1/2 V, that vector in component form, plus W, comma, 1/2 W. Cool so far? All right, next up, what we want to do is what? Well, why don't we add the V and W vector together so that we can get things rolling. So making them one happy vector, we will have V plus W, comma, 1/2 V plus 1/2 W. Now, again, we're going to be separating these vectors at the very end. So we're not going to need to worry about, using the distributive property. Now, this works because of the definition of vector addition. So what do you think our next step should be? Awesome. We've gone from 3 vectors to 2 vectors. Why don't we go from 2 vectors to 1 vector? You have to be careful because you're going to need to put parentheses around the V plus W, all right? And the 1/2 V plus 1/2 W. So we'll end up having U plus quantity V plus W for the first component, and then 1/2 U plus 1/2 V plus 1/2 W. Now we know that the real numbers are associative, right? So what we can do is we can say, all right, this is going to be equal to U plus V plus W, comma, 1/2 U plus 1/2 V, that quantity, plus 1/2 W. And the reasoning for these last two, so this would have been, again, definition of vector addition. This here is because the set of real numbers is associative under addition. And now we're ready for our next move. What's our next move going to be? Whoops. All right. Our next move is what? Awesome. We need to start splitting them apart. So remember, we went from 3 vectors to 2 vectors to 1 vector. Now we'll go from 1 vector to 2 vectors to 3 vectors. And then we'll be done. So let's do it. Using the definition of vector addition, we will have U plus V, comma, 1/2 U plus 1/2 V. That is U plus V, right? And now we have to represent W alone, and that will be W comma 1/2 W. So that's definition, vector addition. Alrighty, and then what's going to happen? Perfect. Now we want to split the sum of U plus V. So we need to put grouping symbols around it. So you got to be careful. Actually, I'll do this. Grouping symbols. So this is going to be U comma 1/2 U plus V comma 1/2 V. And then we have our W comma 1/2 W hanging out. And this again is definition of vector addition. And finally, we'll go from component notation to the original. So this will be quantity of vector U plus vector V, that, and then plus the vector W. And that's what we wanted to show. All right? Awesome, awesome. So, additive identity. The additive identity, remember, so we'll start with U plus the 0 vector, okay? And remember, we want to show that that's equal to U. So, we will have U comma 1/2 U, that's our U vector in component form, and our 0 vector in component form, and this, we're in R2, so it'll be 0 comma 1/2 times 0. All right, so then using what? Beautiful, the definition of vector addition, we'll have U plus 0 comma 1/2 U plus, well, what's 1/2 times 0? It's 0, right? Using algebra. And this was from definition of vector addition. All right, well, U plus 0 will be U. Remember, we're dealing with the components, so we're in real numbers. And 1/2 U plus 0 is 1/2 U. That's just algebra, right? Or you could say identity property. Addition for the set of real numbers. And then that, of course, is just equal to U. So we're all done with the additive identity. Next, the additive inverse. Isn't this fun? So the additive inverse, remember, we want to add U plus negative U, the vectors, and we need to show that that's going to equal to the 0 vector. All right, so first off, let's put them in component form. So we will have U comma 1/2 of U plus negative U comma 1/2 of U. Oops. Actually, that'll look better. All right, so we'll have U comma 1/2 of U plus negative U comma negative 1/2 of U, and that's due to definition of vector scalar multiplication. So next step, what should we do? Awesome. We can use the definition of vector addition to have one happy vector. And so this will be u plus negative u, comma, 1/2 u plus negative 1/2 u. So that was definition of vector addition. And now what do we get? Well, in the real numbers, the real number plus its opposite yields a result of 0, right? That's what I'm going to do for the first one. And then the second one, I'm going to use the distributive property because we can use that where in real numbers. So we have additive inverse for the first part, and then the second part was the set of real numbers are, actually they're both for the real numbers. I'll make sure and put that down. And then we'll have the set of real numbers is distributive over multiplication. All right, we're almost there. So this is going to be equal to 0, comma, 1/2 of 0. And that's due to what? Again, additive inverse for the set of real numbers. And at the end of the day, we'll get, what is that vector? Beautiful, that's the 0 vector for that set. And that's what we needed to show. Cool, cool? Okay, let's get started with the multiplication stuff. Closure under scalar multiplication for our set S. So we use our scalar C times U. That's going to equal to C times U, comma, 1/2 of U. Well, now we need to do what? Beautiful. Use the definition of scalar multiplication, or vector scalar multiplication, to bring the C in. Now, don't assume, that C times quantity 1/2 U is equal to 1/2 times quantity C times U, because we need to manipulate it to make it so. We want the 1/2 first. So we're going to have here, and this, sorry, was by definition of vector scalar multiplication. And this in turn will be equal to C times U. Now remember that the real numbers are commutative, right? The real numbers are commutative, so in multiplication as well as addition. So if we commute the C and the 1/2, we'll have 1/2 times C times U, which is what we wanted, right? Here you've got U times, or comma, for the first component, and then 1/2 of U for the second component. So now, in the first component, we have C times U, so we need a C times U that's grouped after that 1/2. All right? And we were able to do this because the set of real numbers is commutative under multiplication. And that is equal to what? Or not equal. And this vector is a vector in S, the set S. And we're done. That's our closure for scalar multiplication. All right, so next up, we're almost done. 4 more. Distributivity under scalar multiplication. So the first one I'll do is 2 vectors and 1 scalar, and then next we'll do 2 scalars and 1 vector. So let's do it. This one we would start out with C times, we'll use vectors U and V. So putting it into component form like we've been doing, this would be U comma 1/2 U plus V comma 1/2 V. Those are grouped together. Now they're still vectors though, so we can't distribute the C in yet. You have to wait until you can use the definition of vector scalar multiplication. So let's do it. This is going to be C times the 1 vector, which is U plus V, comma, (1/2 U plus 1/2 V. I'm not going to worry about the 1/2 because I think we'll be able to, we're going to be separating the vectors again, so we won't need it yet. So now I have everything in terms of real numbers. So now what I can do is use first I use the definition of vector addition. Now I've got to use the definition of vector scalar multiplication to bring the C in, and then I'll be ready to use properties for real numbers. So this is going to be C times quantity U plus V, comma, C times quantity 1/2 U plus 1/2 V. So now I have everything in the vector, so I can start using properties of real numbers. So this one was definition of vector scalar multiplication. So now, let's do it. Well, this will be CU plus C times V as the first component, and then we'll have C times 1/2 U plus C times quantity 1/2 V for the second component. And that is, we can use that because the set of real numbers is distributive under multiplication. We don't have to say scalar multiplication when we're in the real numbers because they're all scalars. Okay, so now, where did we need to go with this? Remember, we needed to go to this being equal to C times the vector U plus C times the vector V. So I'm going to break up the sum. So I'm going to go from 1 vector to 2 vectors first by using the definition of vector addition. So this will be C times U, comma, C times 1/2 U plus C times V, comma, C times quantity 1/2 V. That's definition of vector addition. All right, continuing. We now almost have it. we need to use the definition of vector scalar multiplication to get this in the right format. So this is going to be C times U, comma, 1/2 U plus C times V, comma, 1/2 V. And that is our definition of vector scalar multiplication. All right. And this in turn is going to be C times the vector U plus C times the vector V, which is where we wanted to go. You good so far? Awesome. You can do it. I know you can. And yes, every step that we did was necessary. Don't skip steps. Err on the side of too many steps. All right, distributivity under scalar multiplication. So that's when you have the C plus D, the scalars, added first, times some vector. We'll call it vector U. So this will equal to quantity C plus D times the vector in component form is U, comma, 1/2 U. Good so far? Now, this is a little tricky. You need to keep the C plus D grouped. You can treat it like it's one constant because we are still in Vectorville. So, when we bring the C plus D scalar in, we'll have C plus D times U, comma, and then the U is the component, first component. And then we'll have C plus D times 1/2 U, the second component. And that was just our definition of vector scalar multiplication. So now we can use properties of real numbers because there's all real numbers in a single vector. So that is what we will do. The first component will be C times U plus D times U. And then the second component will be C times 1/2 U plus D times 1/2 U, where the halves are grouped. Half times U is grouped in each. Cool so far? Now remember, where we want to go is we want to say that we have C times U plus the C times the vector U plus D times the vector U. So this will be, and this reasoning here was why. The set of real numbers is distributive under multiplication. So next up, what do? We split the one vector into two vectors. So we'll have C times U, comma, C times 1/2 U for one vector plus D times U, comma, D times 1/2 U, that quantity. That's definition of vector addition. Alrighty, so then now what would we do? Beautiful. Bring out the C and the D using the definition of vector scalar multiplication. So this will be C times U, comma, 1/2 U plus D times U, comma, 1/2 U. All right, now last step is we'll get C times the vector U plus D times the vector u, which is what we needed to show. Groovy? All right. Next up, associativity under scalar multiplication. So if we start out with c times the quantity d times the vector u, that's going to equal to c times d, and then u in component form will be u comma 1/2 u. And now using the definition of vector scalar multiplication, we'll have c times the vector d times u, comma, d times quantity 1/2 u. Now, using that property again, okay, or that definition again, we will have c times quantity d times u, comma, c times d times 1/2 of u. And this, again, is definition of vector scalar multiplication. And then we'll have, now what property of real numbers might be useful? If we group the c and the d instead of the d and the u, right? Using the associative property for real numbers. So now we'll have c times d and then times u for the first component, and then c times d times 1/2 u, where each of them, the pairs are grouped. And that is, the set of real numbers is associative under multiplication. And then we will have, this is equal to c times d times the vector in component form, u comma 1/2 u. That is definition of vector scalar multiplication. And then finally we will have c times d times the vector u, which is what we were trying to show. Groovy? All right, on to our last one, scalar multiplicative identity. So this is the one where we have to check out what 1 times u, the vector u, equals. And if it equals itself, then it satisfies that. So putting the vector u into component form, we have this here, 1 times u comma 1/2 u. Using, now you can't assume anything, using our definition for vector scalar multiplication, bringing in the 1, we'll have 1 times u, comma, 1 times 1/2 u. And that was by definition of vector scalar multiplication. And then this will be u comma 1/2 u, using some algebra, or you could call it identity property. For the real numbers, the set of real numbers. And then this is just the vector u, and that's what we were trying to show. So what is our conclusion? nothing. So what is our conclusion? We were able to show that every, single one of these conditions were met for this particular set S. So we would say S, which is equal to the set of vectors in the form x comma 1/2 x, such that x belongs to the real numbers, is a vector space. Right? So remember, we said 4 things were required, right? The 4 things that were required So remember, 4 things were required for something to be a vector space. So any vector space has a set of vectors, which we had, a set of scalars, which we had, and 2 operations. So we had addition and scalar multiplication. So here, we're good to go. All right? So next up, in this example, determine whether the set W is a vector space with the standard operations. Justify your answer. So the standard operations are those 10. And what you want to think about is it going to work, right? The last one was kind of obvious, right? Because I had like 3 pages following the problem. So I didn't even ask you too much to think about that. But here, look at this vector. It basically, this set of vectors is every vector in the form where you can have any real number as the first and second component, but the third component always has to be 4, right? Always has to be 4. So here, I don't think that this is a vector space. Why do you think that is? Well, if I wanted to provide a counter example, right, then what I would do is I would say something like -1, 0, 4 belongs to the set W. Would you agree that vector does? Because you can have any real number for the first 2 components as long as you have 4 for the last one. So if we let our scalar C equal to 2, times the vector -1, 0, 4 that has that terminal point is equal to -2, 0, 8. And do you see that this is not an element of the set W because the last component is not 4, right? So we would say no, W equal to all vectors in the form x1, x2, 4, such that x1 and x2 belong to the real numbers, is not a vector space, because what did I just violate there? Closure, right? It's not closed under scalar multiplication. So if any of the 10 properties fail or requirements fail, then it's not a vector space, even if it's just one. This one fails multiple times. So providing the counter example is part of the problem, but the end conclusion is this. Cool? And so subspaces. In many applications of linear algebra, vector spaces occur as a subspace of larger spaces. A non-empty subset of now notice that's a subset of a vector space is a subspace when it is a vector space with the same operations defined in the original vector space. So let's take a look at what we have going on here, all right? Consider the following. The set W is equal to, actually, I don't like how I have that written. That's not written correctly. So we've got, when we use capital letters, like V and W, that is usually used to denote a vector space, okay? So the vector space V is R2, all right? So 2 space. And W, the set W is all vectors in the form where the first component is 0 and the second component is y, such that y belongs to the real numbers, right? And let's take a look at this. Would you agree that, first off, there's certain things, okay? One is the set W non-empty. Does it have at least one element? Right? Yes, it does. Right? It has infinitely many vectors are in there because y can vary as anything, and the first one has to be 0. So if we were to take a look at this, we can answer yes to that. And let's take a look at pictures of it, right? I mean, if you have vectors where first of all, the origin would be there, right? 0, 0. And then wouldn't you agree that as long as x is 0, as long as you're on that y-axis, it's part of the set W, okay? So all of these guys are part of the set W. There's infinitely many of them, right? Okay, so W is non-empty. Now, number 2. Is W a subset, that's the notation for subset, of V? Well, that's really asking us, isn't V equal to R2? And isn't the set where you have any vector that lies on the y-axis, isn't that part of R2, right? So W is a subset of R2. So, yes. Okay? So those are 2 things that have to be part of it. Now, the cool thing about this is you can show that a subset of a known vector space is also a vector space by showing it's a subspace of that set. And once you establish that you've got a non-empty set and that it's a subset of the larger space, in this case R2 is our larger space. Actually, it doesn't have to be larger. Remember, a set can be a subset of itself, just FYI. So now we just need to show closure under addition, and then closure under scalar multiplication. Okay, so let's take a look about closure under addition. Well, remember we have to take something from W. So if we let the vector U equal to I don't know, we can, as long as there's a 0 here and a variable, let's call this one, I don't know, U1, so you don't start mixing up vectors with components of vectors. And let's let the vector V equal to 0, comma, V1, and such that U1 and V1 are elements of the real numbers. And also let's see, okay, so we have it set up, U plus V. Do you notice that both U and V are elements of this set? So let's take a look at what U plus V looks like. So we would have 0, comma, U1 plus 0, comma, V1. That's equal to 0 plus 0, comma, U1 plus V1. And that's why definition of vector addition. And then this will just be 0, comma, U1 plus V1, which is a vector in W. So that's checked off, right? And then lastly, number 4 is W closed under scalar multiplication. So let's check it out. If we let U again equal to 0, comma, U1, such that U1 belongs to the real numbers, and if we let C belong to the real numbers to get our scalar, then C times the vector U is equal to C times 0, comma, U1 in component form, which is C times 0, comma, C times U1. So that is due to the definition of vector scalar multiplication. And that's going to be 0, comma, C times U1. Cool so far? All right. And isn't that a vector in W? So that's checked off, right? So now, what's our conclusion? What do you think? It turns out that W is a subspace of V. So 4 requirements are way better than 10, right? All right, so definition of a subspace of a vector space. We'll get these out here. A non-empty subset W of a vector space V is called a subspace of V when W is a vector space under the operations of addition and scalar multiplication defined in V. And don't forget, you have to also check this non-empty subset part. All right, so there's 4 things you got to check out. All right, so there's a test for a subspace. So again, if W is a non-empty subset, right, of a vector space V, all right, then it's beautiful. You just have to check for closure under addition and scalar multiplication, right? So it turns out that if U and V are in W, then U plus V is in W. If U is in W and C is in E scalar, then C times U has to be in W. Groovy? Okay, so verify that W is a subspace of V. Let's do it. So 1 is W a subset of V? Right? Let's check it out. V is all of R3, and W is the set of vectors where X and Y can be any 2 real numbers, right? The first 2 components can be any 2 real numbers, and the last component is double the first component minus triple the second component. So yes, that is part of R3. So yes, W is a subset of R3. So 1 down, 3 to go. Is W non-empty? Set W non-empty. Well, one way to look at that is the 0 vector part of that set, right? And do you see that it is? So we can say, well, we know that 0, 0, 0 is an element of W. So W is non-empty. So 2 down, 2 to go. Number 3. Let's do. We need to find is W closed under addition? Alrighty, so remember, you gotta identify stuff. So if we let U equal to U1, U2, and then gotta follow what's in the set, 2 times the first component, U1, minus 3 times the second component, which is U2, and V is gonna equal to V1, comma, V2, comma, and then we'll have 2 times V1 minus 3 times V2. And those both belong to W. right? So such that U1 and U2 belong to the real numbers. And we're ready to go on that one. So U plus V equals, putting it in component form, we have U1, U2, comma, 2U1 minus 3U2 plus V1, comma, V2, comma, 2V1 minus 3V2. Now we want to get this into one happy vector, and this will be U1 plus V1, comma, 2U1 minus 3U2 plus 2V1 minus 3V2. Okay, well now they're all real numbers in one happy vector, right? So we can do some algebra, use some algebra properties. So here we go. We'll still have U1 plus V1 here, but we have to have, remember like that other one we were looking at, we have to have 2 times something, right, minus 3 times something else, okay? And so that means that you've got to do a little manipulation here. So if I use the commutative property, do you see that I'll have 2U1 plus 2V1, okay, minus quantity 3U2 plus 3V2. And I can do that because the set of real numbers is commutative under multiplication. All right, so now this is going to be what? U1 plus V1, comma, I can factor out the 2, right, using the distributive property. So we'll end up with U1 plus V1, which was part of the evil plan. And then I can factor out the 3 and get U2 plus V2 remaining. So now I have that format. I have 3 times something, and I have 2 times something. So we can say now, oh, that was because the set of real numbers is distributive under multiplication. And then this is a vector in W. So it's closed under addition. So sorry we ran out of space. I'm going to add a page here for us. So the fourth thing that we wanted to check was, is W closed under scalar multiplication? So let's check it out. All right, so we'll let U equal to the same thing, U1, U2, comma, 2U1 minus 3U2, such that u1 and u2 belong to the real numbers, and we'll let c also belong to the real numbers for our scalar. So c times u is equal to c times u in component form, which is u1, u2, 2u1 minus 3u2. And that's, of course, by definition of vector scalar multiplication. I think I missed something up here. This was because from definition of scalar, of vector addition. All right, and then next line will be what? I got to bring that c in to the vector. So I'll have c times u1, c times u2, and then c times a quantity, 2u1 minus 3u2. All right? So remember, I'm going to have 2 times something minus 3 times something for this to be closed. And I did this by definition. Actually, sorry. This is where this one goes. This was the first step, was just changing it into component form. All right, so now this will be equal to, well, c times u1 is good and c times u2 is good, but I'm going to have to use the distributive property to work with the last component, the third component. So it'll be c times quantity 2u1 minus c times quantity 3u2. And I can do this because the set of real numbers is distributive under multiplication. All right, almost there. So we'll have cu1, comma, cu2, comma. Now we're going to use which one? Beautiful, the associative property. So this is equivalent to 2 times quantity cu1 minus 3 times quantity cu2. And that is legal because the set of real numbers is associative under multiplication. And isn't this a vector in W? In W. So we're good there, right? So all 4 things worked out, and so we've shown, therefore, W is a subspace of V. Okay? All right, so now let's come back to this theorem here. The intersection of 2 subspaces is also a subspace. So if V and W are both subspaces of a vector space U, then the intersection of V and W, denoted by V intersect W, is also a subspace of U. All right? And that wraps it up for this section. We'll be looking at basis and dimension of Rn next time. All right? So have a wonderful morning, afternoon, or evening whenever you are watching this video. And if you like what I'm doing, please subscribe. Bye.